Okay, let me review the very last topic, transformation functions as transformations of the real line. In other words, the x-axis. How the x-axis is transformed into the y-axis. Okay, so pictures are right here. The random one on the left, the more specific on the right. What is doing it here? The comment on the right isn't quite correct. So as you can see, so x plus 1 is the correspondence is, I hope, clear. So 3 goes to 4 like that. So it's clear just from the arrows that the value goes up by 1. The very compact way to represent that is just certainly by a formula. The best way takes care of everything. So we visualize it with that picture on the left, and then next taken to the level of thinking, rather than thinking one point at a time, one number at a time, we're thinking about the what happens to the whole x-axis. Okay, and then we describe it as you can see the shift of the x-axis, but 1 unit. Let's be careful about the direction. 1 unit, either up or right, either way, depending on which way your arrow is located. So depending how you illustrate it with the axis located vertically or horizontally, then it's either up or to the right. Well, there is a subtle point about doing it the opposite way, but we'll talk about that later. At this point, it is if plus means that it's moving up or to the right. Okay, so if it is plus 2, 2 units up or to the right, or generally in the positive direction. Positive direction, and then you have when it's a negative number, you're moving in the negative direction, which would be in this case would be down. Okay, so you'll see those arrows pointing somewhat down. Okay. Okay, so then the next example was a flip. There is nothing ambiguous about that, and once again you see those arrows. They seem how 2 goes farther than 1. And everything becomes upside down, so we recognize this as a flip. So what happens to the whole x-axis? In addition to knowing what happens to every number, we know what happens to the whole axis, and it flips. Okay, it's just like a pin, up and then becomes down. Or it was to the right, becomes to the left. Okay, the absolute value we use to describe a fold. Okay, so that the arrows are right there. So the green is overlaps. So if you start with a piece of wire, you see it on the left, it is orange, a red dot, and then green. What happens at the end, this is literally a fold like this. Orange, red dot here, or turn, and then followed by the green one. Okay, so that's a fold for you. Okay. And then there are a few of these still present, shrinking by a factor of 1/2. When you multiply by 1/2, it means that you shrink it by a factor of half, which is certainly worthwhile mentioning that since we're talking about the whole real line, which has infinite length. If you shrink it in half, how long is it? You shrink the x-axis in half, how long is it? It was infinite. After you shrunk it in half, what happened? No. It is another point is important to emphasize that the shrinkage is uniform. So it's not that we are, I placed x-axis and y-axis next to each other in this particular case. It appears that 0 is not moving anywhere, and it appears that 0 serves some particular purpose. But if you look at it, look at all of these distances on the left are 1s, all the corresponding distances are on the right are 2s. So this is a stretch is by every single 2 points, the distance between them doubles. Okay, so this doubles. The opposite happens when you shrink. once again, every two points, the distance between them becomes half. So it is uniform. Uniform stretch, uniform shrinkage. Okay? So what about the whole thing? An infinite line shrunk in half. How long is it?
Half of infinity.
Which is what? It's still infinite, yeah. It's a trick question. It is discussed, things like that. We'd have to wait until calculus to actually how to deal with infinities. But it's worth mentioning that, yes, as far as the whole real line is concerned, because it's infinite, it remains infinite. So the domain is infinite, a line, the range is still infinite from negative infinity to infinity in either case. So it is surprising. So you make points denser, and yet you have as many points as, and the distance remains the same, distance-wise. Okay, so you cannot tell the difference because it's infinitely many items. Even you have ones infinitely many times, or you add 1/2 infinitely many times. They either way add up to infinity. Okay, so that's the thing about infinity. You can't treat them as numbers. Infinity is not a number. Okay, shrink, flip. Okay, and then non-uniform. The last example was non-uniform stretching and shrinking. So you can see how the purple is stretched non-uniformly. Then in the middle it appears to be the same, and the blue one on the left remains seems to be has been shrunk. So that is a typical situation of functions, non-uniform behavior in different locations. Only linear functions have a uniform stretching or shrinking, depending on that coefficient. In fact, that the slope of a linear function y equal mx plus b, so m, is the stretch ratio. No matter what b is a shift. Okay, worth mentioning. B is the shift. So b is the shift, and m is the stretch or shrink, depending on whether it's larger or less than 1. If m is also negative, there is also flip there present. And so all these descriptions that we have to discuss up to this point was in fact about linear functions for the most part, because only linear functions have this property of having uniform stretching or shrinking ratio throughout its domain. Okay, but it is a very important characteristic of it, and it is a different way of looking at linear functions, as they are literally uniform stretches or shrinking of the real line. Okay, example of behavior that is non-uniform is here. I hope it's here. Okay, here somewhere. Oh, here it is. Okay. Okay. So if we try to combine the 2 points of view on functions, on one hand is the graph, as we have used it a lot, and secondly, this idea of functions as a transformation it's here. Okay, so what I do here is I start with the domain and on the x-axis, and I color it depending on the location. So negative numbers are blue, the middle are yellow, close to 0, and then to the right, everything, unfortunately, the image is lost it lost its axis when I was saving it. Anyway, so you can imagine that there are x's somewhere. So this is the y-axis, and this is part of the x-axis. Okay, so I start with the domain right here, domain. And domain is made of numbers, so and I just color them for the visualization purpose. And then I look at its graph, and what happens to be this shape. Looks like x cubed, by the way. And then what I do is I lift the the domain, that x-axis colored x-axis onto my curve, onto the graph. As you can see, and so, well, just look at it as a stepping stone. And the next, I move to the, and then I may make one more step. And then I push my graph to the y-axis. That's what you see at the last image. So that colorized graph of the function ends up on the y-axis this time. Okay. So this would be the way we used this previously to compute the range. Okay. So the range would be clearly just the whole y-axis. But this time the colors help you understand this as a transformation. So if you look at the last image, the first image and last image, you can see it is a transformation of the x-axis to the y-axis. And judging by the color, you can tell where every location from the x-axis goes on the y-axis. So the yellow goes to yellow, red to red, and blue to blue. Okay, and you can even see some of the stretching and shrinking behaviors. You can see that red, compare red on the left, it is this short, and then red on the y-axis is much longer. So you conclude that there has been stretching of the red. The blue is also stretched. If you look at the last image once again, it is much longer than the original. In the meantime, look at the yellow. Yellow was fairly wide in the original on the x-axis, and the y-axis is very short because it has been shrunk. So as you can see, that's non-uniform behavior of non-uniform transformation or of a function, that it does different things to different locations. Okay, only linear functions behave in the nice manner that everything is the same everywhere. Same shrink, same stretch, same shift. One step further is the same story, but the function is slightly more complicated. And as you can see, that is a literal transformation. So how would you describe this transformation? Stretching, shrinking, what else you see there? What's happening in the middle? So what's happening to the yellow part? So once again, ignore the middle part and consider how you get from here, this is my x-axis, to there, which is the y-axis. So I took my x-axis as a piece of a rope colored in this manner and brought it here as to the y-axis. Okay? So what has happened? Once again, we see the same two features. Red is stretched and blue is stretched. You see it, right? So how short blue was on the left, and now it's long in the last image. Okay, same with the red. What else? What else do you see? What's happening in the middle? Well, once again, think about this as a rope. What? What? You can be more specific. What does this mean? What did we do to the rope in the middle? Well, yes. So this is what we did. Well, maybe they are so far apart that it's hard to tell. So let me copy it. And I'll rotate it. That's what has happened. This is the transformation. Okay. So one line, the original one, marked with X, and the new one marked with Y. What's happened?
It changes direction in the middle.
Right. So we have a word for it. It's a flip. Right. So in the middle, the yellow part actually has been flipped. So this was pointing in this direction, and then it became the yellow part was pointing to the right in the positive direction. Now it's pointing in the opposite direction. How did we achieve that? What's in the middle has happened is a fold. Look at it. We folded our rope. In the middle was folded. Nowhere else it is not folding. The blue part is not folding. The red part is not, but in the middle we folded it together. Okay, so that's what can happen to, that is to be expected from transformations that we see elsewhere. That's what functions do. So we don't expect always to a function behave like this. Certainly not a linear behavior, which is very simple. But this what it happens, and that's what the story of a function that transformation is. It's seen there on the left, and it's more complex. So a rope that can be transformed in some complex manner, stretched, shrunk, folded as many times as you like, and as well as flipped. Okay, so in fact you cannot fold it without flipping. Okay, so any questions about this picture? Okay, and so that's one issue that of complexity that you see with functions when you start looking at them closely and try to visualize them. Another one is when we talked about the sine function, and that is the well, you can see it on the right. This one. No. There is no folding here. This is the sine function, and without looking at the graph, what has happened is I'm not sure if you can characterize it quickly, but we tear. It is more unusual than what we have seen so far, stretching, shrinking, and so on. But it does happen with functions sometimes. The x-axis is torn. Okay. So that is called discontinuity, and you can certainly see why. If you tear, you take a rope and you cut it, okay, before you maybe assemble it in some other way. And that's what you see with the sine function. As you can see, the whole you took that x-axis, okay, and you tore it in three pieces. Okay, so 3 pieces, and they located them at -1, 0, and 1. Okay, so that's the tear that might happen. In addition to collapsing that we discussed last time, the whole bunch of points might be collapsed to 1. So that's actually behavior is the simplest one you can think of. But the tearing is something that if you do mathematical modeling or anything like that, probably something that you try to avoid as much as you can, just like with that example of taxation. Which was 3 tax rates. Okay, if you just try to apply them directly without any kind of adjustment, then you will end up with that story of when you have $10,000 income, and then you get a $1 raise, and then your tax became suddenly $1,000. So then you lose $999. Why? Because of this discontinuity. So I have that picture somewhere. Where do I have one picture of the tax? Yeah, this one. Okay, so if you just take the tax rate as given, it has only 3 values, and as I said, if I was initially my salary was here, and then it became here. As you can see, the tax rate was 0, and then it suddenly became 10%. So no matter how small my raise was, it could have been the raise of $1 produced the tax rate of jumping from 0 to 10%. Okay, so that is something you don't want to happen. So that is why we did extra work with in the second rate, so to make these pieces fit together. So that discontinuity that we can clearly see in the first graph. So there are only 3 values and nothing in between. Okay, so if you think about this function as transformation, then you take everything between 0 and 1, 0 and 10,000, and it goes to 0. Everything between 10,000 and 20,000 goes to 0.1, and the rest of them goes to 0.2. So 3 separate pieces, and you cannot do that without tearing the graph apart. So, and the drawbacks we just discussed. So what do you do with it? You you create a new function that does not tear anything, the function that is continuous, and then the progress of will be reasonable, So as the end result was, if you are moving from $10,000 to $10,001 in salary, then your that only $1 is taken into account when you compute the tax. Okay, so you're paying still 10 cents of that, because 10,000 is beyond the bracket and it is ignored. Okay, so it is deduced from your income. Okay, so that's the continuity discontinuity that becomes a bigger issue in calculus. We just see here as if you think about transformation, you can visualize them as either there is some transformation that might be violent somewhat. So stretching may be hard, maybe folding and so on, maybe shifting and so on, but there is no tearing. Okay, so tearing is bad because it might cause big consequences from smaller events. Okay, so that's what I was. Smaller rise of your income produces large jump in your tax liability. So that is a problem that you try to avoid by sticking with well-behaved functions. Okay. Okay, so it is still to be discussed, and we'll use this interpretation many times in the future once we have more and more functions. And more functions, certainly this is more typically functions will look like than linear. So most of the functions are not linear. Okay, so the next topic is functions with regularities. So linearity is certainly something a regular behavior, but this one refers to functions in general, not necessarily numerical functions. So I go back to this function of this function, and once again I ask what is irregular about it. What is irregular about it, and the irregularity is measured then, not measured, but rather detected by looking at the arrows. Looking at the arrows and how many arrows arrive to each of the destination points. So how many arrows is the question. Let me write it down. So how many arrows arrive at each y. That's what we look at. Not just in case I want to mention that not how many arrows start at each x. Why are we not concerned with the second question? How many arrows start at each x? We have a definitive answer to that. How many arrows start at each x? Just one, right? So that's why we're not concerned. The answer is 1 always. If it's a function, every x has 1 arrow starting at it. However, as far as y's are concerned, that's not necessarily the case, which is what this picture tells us. As you can see, it varies. It varies. So x is on the left, y is on the right, and then we discover the 2 irregularities that I want to point out, and then we're going to discuss them. And that is, well, baseball, no arrows. And secondly, we have basketball. Well, let me use a different color. 2 arrows. So that doesn't mean that this is the function. This is a function, definitely, but it has something that less than regular. A regular function will have like this, all the arrows like this. Okay, so that's a totally regular function, as we have seen it a couple of times like that. If we have x's and y's here, then our arrows might just go like this without missing anything on the left, and there is one arrow per y. Okay, so that's totally regular. Okay, in this picture, as you can see, that's not the case, and these are that can fail in two ways. Then either there is a y with no corresponding x's, so the output for the baseball, there is no one choosing to play baseball on that particular day by these particular boys, and as you can see, there is no arrow riding to it. That's just a way to visualize it, but it is we say that there is no input that produces this output, so it's like it's wasted output. So it belongs to the codomain, but not to what? But not the range, right? Okay, so if we just throw out baseball out of this, it will still work out just fine. So we can, the function still makes sense, right? Okay, so we reduce the codomain and down to the range, and everything is fine. So the second problem is slightly different. We'll get to that in a minute. So let's just examine the first issue. So issue number 1, issue number 2. So issue number 1 is whether or not we miss any values. Okay. So number 1, what if some of the outputs potential outputs aren't actual outputs. So there is no x for this y. Okay, so every time with numerical function, this is an example of a regular function, that's just abstract function, but every time we speak of numerical functions and the range is not all real numbers, we are facing that situation. So y equal x squared, that's a particular example. As you can see, any value of y I pick here, it does not have a corresponding x. There is no x for this y. Okay, so that's a kind of irregularity that there is nothing wrong with it, but we have to point it out and explore a little bit. You can certainly see it in the table. So here, well, here we simply see that y is not in the range. Okay, so that's the easiest way to see it. But you can also, if you go back to this, you can create a table of values as we have in the past. And well, maybe I can find it. It's here somewhere. The table of values. My table of values. Okay, the table of values, and this is the table of values, and this is the problem is visible. This is the problem. There are no crosses under baseball. There are no crosses under baseball. That's if the table of values. If you go to the if you prefer to go to the graph, which is pretty much the same thing. It's not working. Almost the same thing. Whereas the graph is on the left, but then there is no. This is the missing part. Is this? Once again, the difference between the table of values and the graph is simply whether they arrange horizontally or vertically. But as you can see, just there is nothing corresponding to baseball. Okay. Similarly, in the graph that we see here, if I try to find the corresponding value for y, I try to find x, there is none. Okay, it's like doing the, well, it's literally drawing the horizontal line, from that point and finding nothing, finding no intersections with the x-axis, with the graph. So the line, the horizontal line through y has no intersection with the graph of y equal f(x). Okay, when this is the case, that's the problem we want to discuss, and there is a definition here that we have to now put forward in order to have the language of appropriate language that we can later utilize. So a function. So suppose we have a function f from x to y is called onto. O-N-T-O. If there is an x in x for each y in y. Y is equal to f of x. So in other words, we are taking arrows back. So if I have x's here and I have y's there, and then every y I pick, I should be able to find an arrow that arrives to that destination. Okay, so that's pretty much what we are talking about. So so the examples that x squared is not onto. X squared is not onto. As one example. Another recent example that was not onto. What was it? Oh, we had a bunch of them, but well, any one that comes to mind. The absolute value. Okay, the absolute value is very similar. Once again, if y is negative, there is no x for it. Okay. And we've seen actually this shape we've seen many times, and if once you see it, you know that underneath there will be things missing. So y equal x to the fourth. Similarly, though it's not a parabola, technically it looks similar, and so once again our values are missing. Any kind of function that is has holes in it, or then also to be expected to be not one-to-one, well, not onto. Onto functions not too many, but y equal x cubed. The one we just saw a minute ago. This one, either one of these. This one is onto. Once again, the picture on the right indicates that we have covered the whole y-axis, which means that that is onto. This one is not covered in the same regular manner, but once again, every horizontal line has intersection with the graph, so it is onto again. Okay, so onto x cubed, x to the fifth, any odd power will also be onto. Let's not forget all, probably the most immediate example, all linear functions, or the way I put it, linear polynomials. All linear polynomials are onto, but not constant ones. The constant function is f of x is equal to 1. As you can see, that's an example of a constant function, and it's already all the values are missing. The only one value that is there is 1, and the rest of them are not covered. So it is not onto. So it's a typical situation. Okay, so the issue number 1. The issue number 2, as we saw on the picture, is missing values of not the missing values as here, but rather too many values. Issue number 2, there are 2 arrows arriving to to one destination. So there might be some conflict here. If both of them prefer to play basketball, there might be an issue there. Okay, so let me try to make it more precise. It is called one-to-one. So a function is called one-to-one. If there is at most one x for each y. At most, which means that it cannot be 2, but it could be 0. Okay, so there is no overlap between these two. So issue number 1 onto issue number 2, one-to-one, they do not overlap. It's possible to have at most 1, so which means that not 2 or 3 or 4, but could be 0. Okay, so we do not require this to be onto, and the example of such a function is, we just saw it a minute ago. Well, actually, we didn't see it a minute ago. Okay, well, let's think of examples that are one-to-one. Well, first of all, some of them that we have seen, and if we look at the graphs, well, this is actually a good example of two functions that we just a minute ago identified as both of these functions are onto. So this is onto, and this is onto. We know that because the whole y-axis is covered in either case, and every horizontal line crosses the graph at least once. Okay, but what's the difference between these two? What is that flip in the middle, or a fold in the middle, what difference does it make?
If you line up the horizontal line on the bottom, there's more than one.
That's right. So what does it tell you? Using the language that we have learned.
It's not one-to-one.
It is not one-to-one. See, as you can see, there are up to three possible x's. These are the x's corresponding to the same y. Okay, so this is say y, and then all three x's will end up at the same location. Okay, so it's not something that happens a lot among the functions that we have seen so far, but it does happen. And this is an example of, so let me make it specific, an example of not one-to-one. It is y is equal to x cubed minus x. Okay, so well, how do I know this is not one-to-one? How do I know? I can produce an example of y such that there are two or more, say x1, x2, such that f of x1 is equal to f of x2 is equal to y. Okay? Looking at the graph I just showed you, it's pretty much this, like this, with a flip, and a flip in the middle. And the simplest example to pick is simply these. What are those? What do we call them? The graph crosses x-intercepts. Right, x-intercepts. And the value of y is then what's y? And it was 0, right. So y-intercepts are the points on the graph, the value of which is 0. Okay, so if we have more than one x-intercept, it means that it's not one-to-one already, right? So it is a horizontal line. The x-axis is a horizontal line that crosses the graph in more than one location. So all we have to point out to prove the case here that it is not one-to-one, all we have to do is just point out the x-intercepts. So how do we find the x-intercepts? How do we do it? How do we find x-intercepts? This is the function. Well, we know that y is 0, so there. We set up a certain equation. What is the equation? We set y equal to 0, and then, but y is x cubed minus x. So x cubed minus x is 0, and so that's what we solve. And we solve for x. And we just, as long as we end up with more than one solution, remember, it is typically to have more than one solution, then we'll know that it's not one-to-one. Well, this one is not hard. We just factor x out. We have x squared minus 1 is equal to 0. I can factor the one in the middle some more. So what do I get? X squared minus 1, I factor it as what? X plus 1, x minus 1. And that gives me 3 answers. What are the 3 solutions? Corresponding to each of the 3 factors. That's right. 0, -1, and 1. Okay? So these are the 3 x-intercepts right here. -1, 0, and 1. Okay, so we have proved that it is not one-to-one, even though it is onto. Okay, we certainly have seen an example of a function that is onto but not one-to-one. That is, no, the other way around. That is one-to-one but not onto. Have we seen an example of that? Well, let's do a bit more examples of this. So that's to be seen. The graph that has any kind of flip will be like this. This is a sine function. Okay, this one has infinitely many intersections with a certain horizontal line, but not all. So this line has no intersection. And this one has infinitely many intersections. Okay, so doesn't matter. So if there is no intersection, it means that it is not onto. And since it has infinitely many intersections here, it means that it is not one-to-one. Okay, so we don't know which one's which and how it behaves. The issue of onto, at least it is clearly connected to the issue of the range. So the match between the range and the codomain is what tells you whether or not a function is onto. One-to-one is more subtle, and let me give you an example, which points out a function that is one-to-one but not onto. Not onto. So can you think of an example of a function that is one-to-one but not onto? We haven't seen, I don't believe in this class we have seen any numerical functions with that property yet. Well, actually, I take that back. We have seen one, or maybe one more than one. 1 of x. That would work. So 1-to-1. Okay, so first of all, is it 1-to-1? Yes, because horizontal lines have at most one intersection, right? 1, 1. Nowhere it's going to cross twice. The x-axis crosses only once, does not cross at all. So 0 intersections. And that is why 0 intersections means that there is no, so it's not onto. Because now if I look at the range is this, all positive numbers but not 0. So this is the range. Range does not contain 0. 0 is not in the range. Okay, so if it is not in the range, then it is not onto. Okay. Okay, so I'll just stop here, I guess, and then we'll just talk some more about it.